Dear friends, today we discuss two commercially important materials, carbon fibers and carbon steels. The common thread in these two broad categories of workpieces is the role that carbon plays in imparting engineering characteristics to these materials. A carbon fiber is a long, thin strand having a diameter of 5 to 10 micrometers and composed mainly of carbon atoms. The carbon atoms are bonded together in microcrystals that are aligned along the long axis of the fibers. The microcrystals in turn are composed of hexagonal rings analogous to those found in graphite. For this reason, carbon fibers are also called graphite fibers. However, whereas in graphite, the hexagonal array of carbon atoms are in form of sheets, in carbon fibers, they are in form of long ribbons parallel to the axis of the strand as is shown in the figure. The strong in-plane bonds impart a very high tensile strength to the fibers. Carbon fibers are commercially available in form of a continuous tow wound on a reel, one variety of which is shown in this figure. Several thousand carbon fibers may be woven together into yarn to cater to numerous end uses. There are two techniques for the commercial production of carbon fibers: polyacrylonitrile method and pitch method. The raw materials required in these methods, polyacrylonitrile in the former and pitch in the later, are called precursors in the carbon fiber industry. Polyacrylonitrile is obtained by polymerization of acrylonitrile, while pitch is produced by the distillation of carbon-rich materials like crude oil and coal. Almost 90% of carbon fibers are manufactured by polyacrylonitrile method and just 10% by pitch method. The major difference in the two manufacturing processes is that in polyacrylonitrile method, the raw fibers are kept in a stretched state throughout their fabrication, while in pitch method, these need not be held in tension in all the steps. We outline the series of steps that lead to the manufacture of carbon fibers and are common to both the synthetic routes. The first is spinning. This involves the transformation of raw materials into fiber strands. A viscous, syrupy solution of polyacrylonitrile or pitch in an organic solvent like dimethyl sulfoxide or dimethyl formamide is prepared. It is called precursor dope. The precursor dope is passed through the holes of a spinneret. On oozing out of those holes, the solvent evaporates, leaving behind gelatinous fragile threads. These are washed, dried, and stretched to the desired length. Second step is stabilization. The threads are spread out on a sheet called warp. Next, these are loaded on to a set of roller bars fitted with an oven as is shown over here. The strands are heated to 450 to 550 degrees Kelvin for 30 to 120 minutes in presence of aerial oxygen. Hence, this step is also called oxidation. The reaction of oxygen with the fibers causes the polymer chain to undergo cross-linking. This increases the fiber density and hence its utility. The oxidation reaction is exothermic in nature, and the heat generated must be dissipated to prevent overheating and consequent charring of the fibers. At the culmination of stabilization step, the carbon content of fibers is from 50 to 60%, the rest being a mixture of hydrogen, nitrogen, and oxygen. Third step is carbonization. After stabilization, the fibers are heated in absence of oxygen in a series of furnaces each maintained at a higher temperature than its predecessor. The temperature in the first furnace is adjusted to around 1000 degrees Kelvin, while that in the last is at about 2000 degrees Kelvin. Even at such high temperatures, the fibers do not char because of absence of oxygen. However, the non-carbon atoms, hydrogen, nitrogen and oxygen are expelled as gaseous products, and the carbon content increases to almost 95%. At the end of this step, the carbon skeletons are aligned parallel to the long axis of the fibers. Next comes the surface treatment. Before being molded into a commercial utility, the carbon fibers are coated with an organic material. This not only imparts durability to the fibers, but also prevents these from clumping. Coating of fibers comes under the purview of next step, that is sizing. In surface treatment step, the fiber is made ready for sizing. This is done by partially oxidizing the fiber strand using such reagents as oxygen, ozone, nitric acid or sodium hypochlorite. Oxidation roughens the surface of filaments and paves the way for better mechanical adhesion of the coat. Oxidation also converts a portion of carbon skeleton to carboxylic acid functional groups, which in turn react with the functional groups of the coating material, paving the way for better chemical adhesion. The fifth step is sizing. The application of coat after the partial oxidation step is called sizing. In the absence of coating, the fibers tend to become curly and get entangled with each other. The coated fibers, on the other hand, not only remain segregated as individual strands, but also become strong enough so as not to get damaged during winding or weaving. Common coating materials are epoxide, polyester, nylon and urethane. After sizing, the fibers are wound onto cylinders called bobbins. The bobbins are loaded into spinning machines that weave the fiber into yarn. Alternately, the fibers may be embedded with other chemicals to yield a new set of products called composites. For example, carbon fibers may be combined with graphite to produce fiber reinforced graphite composite. We now take up the properties of carbon fibers. The following properties of carbon fibers lend credence to their commercial value. First, a very high strength to weight ratio. Second, appreciably high tensile strength. Third, lightweight and low density. Fourth, electrical and thermal conductivity. Fifth, low coefficient of thermal expansion. Sixth, high abrasion, wear and fatigue resistance. And seventh, corrosion resistance. We now come to application of carbon fibers. A vast number of products and utilities molded out of carbon fibers are ubiquitous, as these permeate into our everyday life. Some of their important applications are now discussed. The first one is textiles. Carbon fibers may be knitted or braided into textile material. Since the fibers possess good thermal conductivity, these are used to fabricate infrared heated clothing and blankets. 2. Aeronautical industry. The fan blades and fan containment cases of modern aircraft are made of carbon fibers. Even the frames of these planes incorporate carbon fibers. In earlier aircrafts, these components were made up of metals or alloys. Their replacement by carbon fibers has increased the efficiency of airplanes in terms of weight per passenger mile. Third, automobile industry. Several internal components of cars like engine covers, seat frames and musical instrument casings are fabricated from carbon fibers. Next, electronic industry. Since carbon fibers are good conductors of electricity, these are used for making microelectrodes which in turn find applications in amperometry and voltammetry devices. Rechargeable batteries and fuel cell electrodes too are made up of carbon fibers. Next is the sports industry. Several brands of tennis rackets, golf clubs and hulls for racing boats are manufactured using carbon fibers. So are crash helmets for rock climbers and horse riders. Motorcycle racing gloves incorporate carbon fiber protectors to prevent tearing of finger ligaments in case of an accident. Next, military equipment. Due to their low density and high tensile strength, carbon fibers are used to make protective helmets for soldiers and flapping wings for surveillance drones. Next, in the medical field, carbon fibers are used as radiolucent materials, since these are transparent to high energy rays. For this reason, they are used in components of X-ray machines and radiation therapy equipment. Robots for some of the operations are also made up of these fibers. An important medical use of carbon fibers is the fabrication of artificial limbs, also known as prosthetics. Next, power generation. The blades of modern windmills are constructed from carbon fibers. We now discuss the advantages of carbon fibers. Carbon fibers have the following merits. First, long working life. Second, greater compressive strength than nearly all other reinforcing materials. Third, insensitive to changes in temperature. Fourth, lightweight. Fifth, lower density than steel. And sixth, potential to replace metals in many utilities and provide a better service thereafter. Carbon fibers have a few shortcomings as well. Firstly, carbon fibers are brittle and under strain tend to develop internal cracks. Secondly, carbon fibers have a higher cost than the materials which they tend to replace. Thirdly, the organic coatings applied during the sizing stage of manufacture are sometimes toxic in nature. We feel that this module on the significance of commercial importance of carbon fibers will be incomplete without the story of a sportsperson, Oscar Pistorius. Oscar Pistorius, a South African national, was born in 1986 with a disease of limbs called fibular hemimelia. When he was 11 years old, both his legs were amputated halfway between knees and ankles and replaced by prosthetics made of carbon fibers. Yet, during his student days, Pistorius excelled in athletics and was selected to participate in 2008 Summer Paralympics held in Beijing and then in 2012 Summer Paralympics held in London. He won 2 gold medals in each event. Later, however, Pistorius became a subject of controversy because of claims that his artificial legs gave him an edge over runners with natural legs. The claims were not totally unfounded. During surgery, Pistorius' ankles and feet were substituted by J-shaped carbon fiber prosthetics called flex foot cheetah. The carbon fibers in this brand are so arranged that the prosthetic stores kinetic energy from the wearer's steps as potential energy, much like a spring. When the need arises, the potential energy is reconverted into kinetic energy, enabling the wearer to jump and run at a fast speed. Ideally, the matter should have been debated further. However, the controversy died down because the sporting career of Pistorius ended abruptly in 2014 when he was convicted of murdering his girlfriend. Steel is the most important ferrous material that has day-to-day applications in modern society. It has two subclassifications, plain carbon steel and alloy steel. Plain carbon steel contains only carbon and iron, while in alloy steel a number of other metals like manganese, chromium, and so on are also added as integral elements. The constant range of carbon in both types of steel is same, that is 0.2 to 1.8%. We will be mainly discussing plain carbon steels today. The term plain carbon steel refers to a variety in which the maximum proportion of carbon is 1.8%. It is also called carbon steel. We now take up the classification of plain carbon steels. There are three main types of plain carbon steels. First, low carbon steel. The amount of carbon in this type is in the range of 0.1 to 0.3%. It is used for making kitchen appliances and cans. Second is medium carbon steel. The carbon content in this variety varies from 0.3 to 0.8%. It is used in forging equipment and automobile springs. Third is high carbon steel. It contains carbon in 0.8 to 1.8% range and is used in cutting tools and high strength wires. Let us now take up the properties of carbon steel. As the carbon content increases, the plain carbon steel acquires increased number 1 hardness, number 2 tensile strength, number 3 resistance to wear and abrasion. But what decreases is the ductility, toughness, machinability and weldability. Let us now take up the drawbacks of plain carbon steel. Plain carbon steel possesses number 1, poor impact resistance, number 2, poor corrosion resistance, and number 3, poor resistance against oxidation at high temperature. We now describe a special type of carbon steel called Wootz steel. This is a variety of steel which originated in India, and to be more specific, in South India in the 6th century BC. It had several alternative names, including Hindvi steel and Hinduvani steel. Its metallurgical processing was devised by Shiva dynasty of Tamils in Kodaimanal in Tamil Nadu. Later, another production center was established at Golconda in present-day Telangana. Wood steel used to be prepared by first hammering out slag from wrought iron and then stirring the melt in large clay crucibles with bamboo sticks. The bamboo sticks added carbon to the base metal. The addition of carbon resulted in the formation of iron carbide called cementite, Fe3C, which manifested itself as wavy strips in the finished product. This manufacturing process was called the Milcam method. Wood steel was mainly used to make knives, daggers and swords. It is believed that the wood swords were so splendid that in the 19th century battles for colonial expansion, the English soldiers would often swap their weapons with those of the defeated natives. With the advent of Industrial Revolution, many new materials came to the fore. These included tough metals, alloys, and composites. These engineering materials had wide range of applications. And in order to fulfill the needs of the society, these materials had to have wear resistance, fatigue resistance, corrosion resistance. They also had high strength, both tensile as well as compressive. They were strong, they were hard, they could even be used as cutting tools. All these materials had very long working lives. They could be retained in their form for many years. Carbon plays a strong role in these engineering materials. It was an ingredient of steels, rather a large number of steels, some of them containing only carbon and iron. They were called plain carbon steels, and others had a few other elements like manganese and chromium in addition to iron and carbon. They were named alloy steels. Alloy steels had better applications and better utility as compared to plain carbon steels. However, for arriving at alloy steels, the first step was to manufacture the plain carbon steels. Today, steel is ubiquitous. Right from household to sophisticated engineering applications, many materials are made up of it. Similarly, carbon fibers have proved to be very useful in modern society. Whether it is the electronic industry or the automobile industry or the aircraft industry, carbon fibers will be found everywhere. In sports, most of the equipment are made up of carbon fibers. In windmills, the blades are made up of carbon fibers. What is important is that these materials are not an end in itself. They are being continuously changed to meet the future uses of the society. Their composition is being changed, their shapes and their geometries are being shaped, and as new and new material comes, we will keep updating you.